Good morning, everyone.
Morning.
Our today's webinar about processing rasters from satellites and drones, and a few more things. This webinar is based on our World Tour materials, plus some new and very cool stuff, which Dean will show in the second half of our webinar.
Yeah, we gotta update things a little bit to keep it interesting.
Here is this pretty bold statement. Why do we care about rasters? Because they're as important as bread to a sandwich. Well, during the World Tour, I made even bolder statement when I said we don't care about rasters. We really care about bigger things like, I don't know, our community, our career, our children, or a new car. To make, to achieve our goals, we need to make proper decisions based on proper information. So maybe we care about, professionally about land use, or maybe city planning, or power line maintenance. For that, we need really up-to-date information, and rasters is are really good for delivering really fresh, high-resolution information regularly.
Yeah, and given the nature of the platforms, rasters allow us to collect a lot of data in an automated way. So we can have sensors out there that are continually collecting data, and that's why rasters can be very handy.
Yeah, and you will hear us repeating the word automation and showing how we automate the raster processes that we show today. A little bit what is new in 2018. We added a few new readers, as usually. Among them, GDAL-based raster mosaic. Then those 54 maybe less known raster formats based on GDAL library. PDF reader is a big one, but it contains everything. We can read text, we can read rasters, we can read tables from PDFs, and in a week we'll have a PDF reading webinar where I will show a few interesting examples of processing PDFs. So you can sign up for that one too. Then these two new transformers. Dean, would you like to say something about these two? Because you really advocated for them.
Yeah, we were waiting for these transformers for quite a long time. For the stats calculator, I had one on the hub that was based on the point cloud stats. So it was good to actually get an official raster stats calculator, and that can be very handy for automated processing, because you can look at the character of a particular raster and filter it based on that. The convolver, that's really more. There's the convolver. There's a number of names for that. There's lens functions or focal functions, and that's basically processing your raster based on its neighbors. So each cell can be processed based on some character of its neighbors, and so you could do things like blur, edge detection, classification. Many functions can be built on that. So we're looking forward to seeing what some of you more creative raster keeners out there might come up with the raster convolver. There's a lot of probably follow-on transformers that can come from that.
So speaking about remote sensing, what we can bring to your workflow are images from Landsat and Sentinel, which we showed a lot last year. So this year we talk more about planet imagery, and my examples are based on this platform. Dean will be talking about the information from drones, but basically it can be anything. Dean has a very, very cool example. I think you will mention it later, how people use just their cell phones to collect, let's say, airborne imagery. Then, and probably you might find interesting what is coming in 2019. DICOM medical imaging, and I have a 2 GB archive sitting on my laptop waiting for me to play with those images. It will be really interesting to see what we can get from them. Then OGC WCS.
That's maybe web coverage service. So basically, people are more familiar typically with WFS, WMS. The issue with WMS is it actually just gives you a picture of your map data. It's not actually georeferenced. So the coverage service, there's a lot of applications there, both imagery, DEMs, and others that could be quite useful for.
So cesium ion, it's more about not getting rasters into your workflow. Maybe it's publishing 3D raster and point cloud information to cesium platform, which is interesting and quite impressive what you can achieve there. I tried it with 3D buildings, loading 1.2 million buildings into cesium, and it was like really interesting, fast, and impressive, and it works just in your regular browser. So, and then raster object detector, it's a transformer which is coming. It is based on OpenCV, and it allows you to train the transformer on particular images to extract the same kind of information from other images. For example, you can show, a few faces, like not in a geometrical sense, but in human sense, and then this transformer will detect faces on other images.
Very cool. And overall, there's a number of improvements, both in 18 and 19, on improving performance. So there's always a lot of good work going on in the background to improve stability and performance.
So for processing rasters, we have lots and lots of useful transformers, I think about 50. But I would like to talk maybe a little bit about 4 of them. Here you can see feature reader, and you can say it's not even a raster transformer. Yes, but it's very helpful for reading raster information. And why feature reader is better than, for example, a normal reader. So maybe I'll switch to a workspace and show you how it works. So maybe here. No, not here, here. So if I add, for example, a planet reader, because, well, my examples are based on planet data, you can see that we have to pick a certain date here and then start and end for which date range we would like to get the information. Then we have to pick the assets from a fixed list, and then we have to type some JSON to apply certain filters to what we read, for example, cloud coverage or data coverage, as opposed to no data pixels. So with a feature reader, I can use, I can create, for example, a date attribute and read it from a database or from any other data source. I can specify, for example, a period, so it can be very driven by your data, not by whatever you type. Then I can have a JSON templater here. I can create a JSON expression only once, and then insert my parameters inside this template, which we specify at the beginning of the transformation, and that will be passed to feature reader in here. Yeah, so I specify start and end date. Here is my JSON filter, and so on. So another very good thing about feature reader is that you get out the initiator, the feature that entered the transformer. It also leaves it, and it says how many features it read. So, for example, in this case, I tried to read rapid eye, or maybe planet scope, doesn't matter. So one of the data sets, and if we don't read anything, then we can try to read something else, a different data set. For example, smaller resolution or older, so something. So this way we can always fall back until we get something useful. Another transformer I wanted to mention is raster mosaicer. So when we bring a lot of information together, a lot of rasters, it's a good transformer to use to combine it together. And in 2017, I think we added a few good things to combine them together. So, for example, the last raster could win, or the minimal value can win. So, for example, if you have cloud coverage and the surface, and you put one on top of another, your surface, which is usually darker than clouds, will win, and you will see not the clouds, and so on. So another good transformer is Mapnik rasterizer. I use it a lot for a lot of different things, for making beautiful maps, but even for making Christmas presents for my friends and for my family. I use it in one of the workspaces I showed today, one of the workflows. And finally, NDVI calculator. This one is green, and you probably know this is as a custom transformer. And I show it not for NDVI per se. I show it to illustrate that you can, if you know some math behind certain algorithm, then you can wrap it up into a custom transformer. Moreover, if you have some third-party tool, with the command line interface, you can wrap it up into a custom transformer and have that functionality within FME. And Dean will show that in his presentation, in his part of the presentation. So, and of course, because we deal with huge volumes of data, so Planet collects probably millions images every day, it is not possible anymore to deal with this information manually. You cannot just go, set it up, download, and process, see what you got. You have to automate it. So, and FME is really great for automating these processes, which I hope to illustrate today. So, and we come to our first demo. We will show how we make a daily update for a hybrid map, which combines planet imagery and some vector information. This is the workspace actually where I showed you at the beginning. It's how I read this planet imagery, and then I upload, I mosaic it, upload it to S3, the image, and then that's the part of processing the image. And then I use Mapnik rasterizer to make a really nice overlay. So in this case, I read planet imagery plus San Francisco Transit Authority feed JSON files, which basically represent all the bus routes in San Francisco, and I overlay on top of the imagery and rasterize it here, create tiles, upload them to Amazon as tiles, and the result looks like this here. So I was a little bit too generous with my cloud filter. You can see that I allowed this cloud to this, but you can see, so it was updated on August 12th. With Planet imagery. If you sign up for a free license, you get a 2 weeks delay. If you sign up for paid service, then you get the freshest, the daily updates, so every day. So I prepared the service in April 2017 and didn't touch it since. So it just keeps working, and every day we see the updated. Well, every day when the cloud filter is good enough to pass to allow the data pass through the workspace. And you can see we have all the bus routes and cable routes on this map. So then you can bring any of your data, combine it with rasters, and run it daily, scheduled or somehow else, and have your fresh map every day. So now, but what if you need millions of tiles? That would take a long time to process. So this laptop probably would create 1 million tiles in maybe 2 days, maybe a little bit faster, but that might be way too long. So in January, we made this experiment about generating millions of tiles much faster. So that was work of made by Don and Grant, and I was just basically trying to process to use their system to create a lot of tiles. So I go back to my browser and switch to this map. Believe it or not, this tile set has 1 million tiles. It's Greater London area from OpenStreetMaps. I basically again used Mapnik rasterizer to create these tiles, and then I executed 100, 200 machines, 3-4 engines on each, so 400 processes, and those machines do not exist before you ask the process to run, and they don't exist after you've finished. So they are created and then killed at the end, and you pay only for the time that they actually live. And I was able to create this data set, 1 million tiles in 25 minutes. I really wanted to make it 20 minutes because, well, somehow it sounds better, but, well, it takes some time to execute all those machines, and then some time to shut them down.
So that's not too bad, though.
Yeah, 25 minutes, I think it's pretty good, yeah, instead of, say, 2 days on this laptop. So that's my first example where we go from where we basically daily update our background maps and forget about the old data. So how about collecting data over time so that we can bring it together and analyze, compare, at least visually, some data from the past and more recent data. So this is another example I have here, where I again read some planet data. Here I just download some thumbnails, some previews to see whether I have enough coverage in the area of my interest, and if I have enough data and the cloud filter is good enough, and then I download real data and generate a few products. I generate normal RGB geotiff and analytical geotiff, which contains infrared information, and also some PNG files, which I can store somewhere in the cloud and make them really easily accessible for visualization and comparison. So here I create NDVI, and for those who don't know what NDVI is, it's Normalized Difference Vegetation Index, and it shows how healthy your vegetation is. So live plants have this property. They really like light that, well, we see with our eyes, and then particularly blue and red, and they don't like green. That's why we see all the plants green. But they cannot use infrared radiation for photosynthesis. So, and it can be harmful for them. So they did bounce it back. So and there's the really sharp difference between red consumption and infrared reflection. So based on that, you can basically see how healthy your plants are. Beside that, I also create here infrared image and just normal RGB image.
Is that a very complicated formula?
No, the formula is very simple. I actually can go to this transformer and show how simple it is. Well, of course, reality is always a little bit more complicated than that. Because you have to normalize everything for the top of atmosphere, but, well, we don't go into those details. But the formula itself is as simple as this: subtract red from infrared and add and divide it by the sum of infrared and red. So that's how simple it is.
Cool.
So, and now I will show the results. Again, I make it into a web service which runs daily and collects the images over time. And I started in 2016. Well, I went back a little bit to have data from 2016 up to up to this day. Here is the start page, and as you can see, they are all published. You can go there, you can play with it, and you can download and adjust it for your workflows. You don't have to work with vegetation. You can use it for water detection or snow detection or for anything else. So I can pick here 2 dates, for example. Let's compare. Let's go from March 2018 to, well, whatever the latest image is. As you can see, it's August 13th. And this creates pretty quickly. Shows us all the thumbnails starting from March and to this date. and I can say, show me how it looked on August 13th, and I can compare RGB or normal visual image with infrared. And you can see, for example, this little thing here, you don't necessarily recognize it as water, but in infrared it's very clear where is water and where is vegetation.
Or it could be vegetation with water within it or something.
Yes.
Like wetland.
Yeah, for example, you hardly can see where the river flows, but in infrared you can clearly see. Basically, you can digitize using infrared images. And I also calculate NDVI. You can see where the vegetation is the healthiest. It's blue. Then red is really bad. So it's probably just fields. Yeah, you can see that where it's field and so. And what is more interesting, you can go back and compare something in, say, April versus August, and you can see where something grows, where something was harvested. So, and I think you can, for example, easily draw a polygon around a certain field and calculate daily just a number based on, well, point cloud raster statistics calculator. And you don't even need the raster, you just need that statistical number, which will tell you how this field is changing over time. So, and if you see some bad trends, you may, well, need to act somehow.
Yeah, you could even automate that and have an expected range, and then if it goes outside that range. Yeah.
So, and this page is generated with FME. So I just have some attribute creators with HTML and JavaScript inside, and it's just a workspace. You can see here in the command line that this is a workspace with some parameters. Well, basically two parameters, from date and to date. So, and whenever I click this button here, this workspace executes and generates this page with everything.
And what's the name of the transformer that makes that page?
It's just attribute creator.
And the HTML.
No, I don't use it. No.
Oh,
it's just
okay.
yeah.
Just have a
well,
template.
yes. We are thinking about making our HTML generator a little bit more powerful by allowing him deliver much more different visualization tool, but well, it's a work in progress. And we should say thanks to Greg Patterson, who created this slider, and I think you will enjoy. You can basically put any images into this and have it for your purposes. So now I go back, and yeah, here's this slide. The last one is making georeferenced satellite videos. I played for a few months with what we can do with video, and now we plan, but well, it's still work in progress, and probably it will take some time before you'll see it as a standard capability in FME. But we can do a lot with videos if we combine FFmpeg program integrated with FME, and we can basically take all the power that FME has in spatial world and pass it to videos. For example, we can easily georeference videos, and again, I will go to this page, and well, it runs really smoothly on my laptop. You probably don't see it as smooth as I, but you will get the presentation afterwards. And here is the link. You can basically simply go there and see a really nice and smooth video. So this video, as you can see, it's georeferenced, and you can pan, you can zoom, and it keeps playing. And really, it's really interesting and powerful. And you can see, I actually never saw California green in the past, because I always go there for Esri conference in summer and always see it like you can see it now, but not like this, never green. So of course, all those workspaces are available, and you will get them after the webinar, and you can see what you can do, how you can play with it, what you can take from this to for your own purposes. And after that, I go to my slides and pass the microphone to Dean.
All right, thanks, Dimitri. Yeah, some pretty amazing stuff there, looking at how we can use FME to consume real-time data or data that's in a time series, time step, getting very current data and extracting value from it. So well, I'm going to kind of switch gears here a bit, partly because I like to have a lot of fun with UAVs on my own, but also because I think it's a very interesting platform. So far we've been looking at collecting data, a lot of it's satellite-based or perhaps air photos. So from a high altitude in a very kind of regular structured way. So what happens if we need more local scale data and in a way that's more customizable way of collecting data and on a low cost platform? So there's lots of applications where, okay, it's great to have satellite data, but something changed on the ground. It could be something as simple as a construction site that you want to map out, or it could be a disaster response, like some of the examples I'll show in a minute. So I think UAVs is a great platform for data collection and also for automated data collection, because a lot of the platforms are relatively easy to automate. And I think that's going to really revolutionize geospatial data collection at the local level. So first of all, just looking at the overall life cycle of, or sort of work cycle when you're flying UAVs. I got this snapshot from, or I got the graphic from Renato from Alabama Power from one of his presentations we did together. And the basic idea is, you keep going through this same cycle. So you've got a plan, your mission, then you fly it, and then you review, collect the data, and then often you keep repeating that because you missed something or you got to move on to the next field or the next area that you're surveying. Now the planning part is important because it reduces risk. You don't want to fly into buildings. You don't want to put any personnel at risk, and you want to make sure you're compliant with the local flight regulations. And it also helps optimize your workflow, so you don't have to go resurvey places because, let's say, you didn't have enough overlap between images. And one thing, and again, Renato showed us this in an earlier presentation. He made a KML tour, so it would actually, he used FME to generate a KML tour, which would sort of do a flight preview. It would fly the whole thing, and you could just watch it in Google Earth and make sure that everywhere you were flying was safe. Then actually, in terms of flying it, we can use FME to generate the missions for tools like Litchi, which will feed that telemetry into the drone, and it will run the whole thing via autopilot. So we can use FME on the planning side to review the flight plan before we do it. We can use FME to generate the flight plans, and then ultimately the post-processing. FME has a lot of tools to support that. So whether it's the georeferencing, mosaicing, and generating point clouds, what have you, and then all that post-processing, and ultimately delivering that data, so uploading it, be it to the cloud or making it available on a geoportal. So we'll look at some of those steps, but obviously today I'm not going to we don't have time to focus as much on the planning and flying because our main focus today is on the actual products, the raster. So here's a quick example, but before I jump into this, I'm kind of living on the edge here a bit, so if things kind of go south, I have a video to show this, because even if this does run, depending on how many things I'm doing at once, it may or may not complete in time. So I'm just going to go ahead and run this. And so this is my second example. I'm going to run a Docker image, and I'll explain what this Docker is doing in a minute. And right now, I'm just going to show you, I'm going to kick this thing off, and I'm expecting it to fail at the first go around, because I just wanted to show you that I do have some error detection on this Docker. on the Docker run workspace or on the custom transformer, and it says, oh, some of your output paths aren't empty. So what I have to do is I have to go into my output folder and get rid of the previous run. And then I can go ahead and kick that off. And I'll explain all what's going on here in a few minutes. But basically, the custom transformer has parameters for things like the output resolution, the output path, or the project folder, and number of overlaps, number of CPU cores to use, and stuff like that. So that's going to be running in the background. It takes about 5 minutes to run, presuming everything does what it's supposed to. And I'll make sure I don't get a error message here right at the outset. So it's actually got Docker running locally. Everything here is locally on this little light notebook. So we'll see what happens with that in a minute. So back to the presentation. And let's talk first about the, first we'll talk a little bit about an emergency response example for search and rescue, and then I'll get into a disaster response. So I guess the main point here is that I published a custom transformer with a UAV mission planner, which generates missions in the form of Litchi. So it's just a CSV file which feeds into the Litchi portal, and then you connect your mobile device to that to upload the mission to your drone, and off it goes. I will say that it does, the first few times you do that, and you see your drone take off and fly away, it does take a little bit of faith to hoping that thing comes back. But anyway, the whole idea is you keep a visual line of sight. If it does go too far and you don't feel like it's doing what it's supposed to, you can cancel the mission and it'll return home. But yeah, it's interesting to see off it goes and flies the whole mission. And then the post-processing. So we'll look at that. So on the left here, you can see there's a link to that UAV mission planner on the bottom left there on FME Hub. That generates a Litchi format file, which you can then via Litchi upload to your drone, and it flies the mission. And then on the post-processing side, what it's doing there is just geolocating each of the output images. So it's not a full ortho rectification or mosaic process. It's just overlaying it. But as you see, when we zoom in here, and I'll pop this up in Google Earth in a minute, that kind of geolocating is sufficient for this application. So this is not really a mapping application. Here we're just zooming in, and we're looking, we want to rapidly make these images available to look for, say, a missing boat or a missing person. And so you can see in this case that that seagull in the bottom center, which is clearly visible on the UAV imagery, but is not obviously visible in the Google Earth background map, because of course the big difference there is Google Earth, you know, the UAV imagery is a little bit more current. So here we are zooming into where our current office is for now. That's going to change. We're going to move a little bit north of that in a couple months. And then we'll look at, okay, where is the survey data? And I'll just zoom down here into what's called Mud Bay or Boundary Bay. So this is where I did this test survey. This is just a test survey for evaluating this for potential use in search and rescue. And if I look here, where this little bit of a reef island is, you can make out that where the seagull is, and you can also see this navigation marker, which doesn't even show up on the satellite imagery at all. So if I just turn that off, you can see there's nothing. There might be a little speck there, but it's not identifiable as a nav marker. So overall, I think that's pretty useful. In this particular case, I think the UAV platform is very valuable, because if you look at this bay, there's a lot of it that's just mud, very shallow, and so our boat actually can't even get in there. So people can't access it by land, or or by sea, unless you have something like a hovercraft, in which case you got to wait maybe 45 minutes for them to show up from YVR, where they're based. Okay, so that's a search and rescue application, and most of that automated, both the mission planning, flying it, and the post-processing. So back to slide deck here. So now let's look at some disaster response applications and challenges. So here are just a few high-level comments about disaster response in general. Obviously, we need very timely data, and that's why raster is valuable, because a lot of the methods of collecting raster data are much more automated than would be for typical vector or base map type data. And FME is very useful because it allows us to bring all that together. So when you bring in raster data, it's good to have access to things like OpenStreetMap, because you can have a background to make sure things are properly geolocated. And so often in a disaster response situation, you're getting data from many different formats, many different forms, and you've got to mash it all up, make that sandwich that Dimitri showed us right at the beginning. And so some of that will be old data, some of that will be brand new data, and bringing it all together. And the other thing to remember in a disaster response situation is often you have very limited IT infrastructure, and so you've got some serious constraints there. And then on the flip side is when you do collect data, you've got to make that data available, because often there's crowdsourcing or a lot of people that are working off-site that need access to the data. So even though you have limited infrastructure, there's a lot of pressure to get your data maybe uploaded somewhere so that other people can support and make use of it. And of course, you want to share that data with the other relief agencies that need to use it as well. So, and lots of room here for automation. So let's look at a quick example from Southern Co. and Alabama Power, which Southern Co. is the parent company. And what Renato and his team have done, they've got 50 or 60 UAV pilots now working with UAVs. So they use UAVs for their regular inspections as well as for disaster responsers. In this case, storm damage assessment. So in the past, they would have to either get people there on the ground, which obviously is time consuming, or they would have to get helicopters in there, which has risks of its own, because of when you have storm damage, you got power lines and towers that might be at odd locations, and so it's a messy environment. So UAVs are a lot safer and easier to deploy, and also allows them to rapidly collect data and assess what the storm impacts are. And then when they find, okay, these are the areas where the towers are down or the lines are down, they can then target those areas for maintenance to send their people out. So that way they can guide their response to the storm damage. And I know they also, Renato told me they sent a team over to Puerto Rico to help with some of the storm damage response there as well. Now I'm going to mention a few words about Global Medic. So they're a great outfit, kind of a homegrown Canadian-based humanitarian agency. They do disaster response around the world. They've been on almost 200 missions, 190 plus, and not all with UAVs, but overall they've had close to 200 different responses. And so they have a fairly new UAV program, but they've already been employing UAVs for looking at things like building damage assessment and also transportation infrastructure damage assessment, because obviously if bridges are down, you don't want to send your relief trucks and then they all get backed up, they can't get across the river, so you want to find a location where they can get through. So that thing that popped up, that was just the end of my Docker run, so we'll look at that in a minute. Yeah, so basically been working with good colleagues there, Brett and Francois, and so they're evaluating a number of different tools to support automation, and a number of, including FME, Open Drone Mapper, Pix4D, 4D Mapper, to name a few. And of course, the idea with FME is we're supporting the automation were sort of the glue to integrate a lot of those tools together and also publish the results. And so one of the things that Brett told me that he ran into in the Guatemala volcano response is that because they were using Pix4D in the cloud, he was having to drive 2 or 3 hours a day just to get somewhere that had enough bandwidth to upload the data. Then, of course, he has to wait for the data, an hour plus to get the data uploaded, processed, and then a bunch of time to download and stuff. So a lot of time spent traveling and waiting for uploads and downloads, trying to use cloud infrastructure. So in that case, they would probably be much better suited to have local processing capability that they can do at least some preliminary processing. Now, some of those online tools might give you higher resolution, or they may have specialized information extraction, but we've been doing experiments with Open Drone Mapper, which is a free open source tool available in Docker. And I think in this particular case, it would be a great application because it would allow them to process the data locally, at least for basic orthomosaics and point cloud generation. So that really underlines that poor bandwidth. We can get very comfortable doing everything in the cloud here at the office, let's say here at SAFE, but there are lots of applications where people just don't have the kind of bandwidth that we have here. But yeah, just a nod to GlobalMedic for the great work that they're doing, and you can find out more about them from globalmedic.ca. So let's jump in and look at this hub, the example that's available, Open Drone Map Caller from the hub. And I will just go ahead and minimize this and pop up the workspace. So not a very complicated workspace. I think it fits Don's 10 transformer rule. Of course, the caller itself is a little bit more complicated. And as I showed you earlier, it's got some basic parameters for setting things like what's your desired resolution. There's also some parameters there that you might have to read up a little bit on the algorithms in order to understand how best to use them. Things like mesh size and octree depth. So there's a lot of interpolation algorithms going on behind the scenes. And so this is what I'll just briefly look at this. I know we don't have a ton of time, so I won't get into a lot of detail. But you can see here, there's really two main parts to this workspace. The top big bookmark, all it's doing is analyzing your environment and reporting on any errors. So this workspace is essentially a wrapper around the Open Drone Map Docker image. And so what it's doing is, for example, it's using a feature reader here to look at your directory and make sure that you have source data there, that make sure you actually have images. And you can see earlier when I had that error, the output folder is already populated. Well, it won't overwrite data, so it just reports an error and stops at that point. So, and I also check to make sure you actually have right permissions. So there's a bunch of stuff going on there on the top half as a wrapper, just to make it a little bit more user-friendly. And then the bottom half here, what we're doing is building the Docker run command with your path and your runtime parameters, like the resolution, mesh size, and things like that. So that's that actual Docker run command. And that's about as complicated as it gets. So we're just using a system caller here. There's no Python, at least there's Python within the Docker image, but not here. And then based on the return code, I can tell whether or not, let's say, Docker's running or not. And so that will come off the return code. In this case, 0 is successful, and then it writes out the result. So this is all available online on the FME Hub. You can download and play with this. And I think it's an interesting example of using FME to wrap up a Docker instance. And there's so much power in that, and being able to automate that, I think it's pretty exciting. It's not just for raster applications, but for a lot of other types of geoprocessing. So let's look at the output. Got a Mapbox background. And you can see, you know, the background's not super detailed, but you can see the geolocation's not bad at all. And we'll just kind of, I'll turn off the point cloud for now, and you can see, you know, zooming out, the overall context of this thing is Mud Bay, the northeast corner, and then zooming in, we've got that railway track, and yeah, there you go. So that's what the mosaic looks like. And if I actually take a quick look at the source data, and I just grab any one of these images and drop it in, you'll see that actually, I'll drop it in here, it's probably better. So there's absolutely no georeferencing in the source image. So it's just a raw source image, coordinate system unknown, and it just has, you know, 3,000 by 4,000 pixels. That's it. So so the amazing thing about what this Docker image is doing is that it's actually doing, it's using the EXIF tag information, so you can see the lat long information on the JPEG. It's basically using all of that information plus focal length and everything else to interpolate where all these images are and then mosaic them together in this relatively seamless output. And when we look at the point cloud, you can see that, okay, there are perhaps a few gaps in there, so you could maybe add a little bit more imagery to it to fill in those gaps. But by and large, not a bad output for, you know, something that in the past might have been, you might spend $50,000 to hire a plane and fly this area, and now with simply just with a drone and with open source software, you can do it, you know, relatively quickly. So hang on a sec here. I think it's just catching up with me a bit. So yeah, so it's pretty exciting what's possible with FME and with tools like OpenDroneMap. Here, I'll just pivot this over so you can actually see the 3D aspect of it. And there's a link in the presentation to a little video on YouTube, so you can actually see, you can play around, or you can actually see this 3D view of the data in that video. Okay, so just popping back in the couple minutes we have left to wrap up. So that was the running that on Docker, and you can just to show how this whole thing finished. There was the end of the Docker run, the OpenDroneMap caller. And I will make a note. I will mention that here's a shot of that source data again. You need a lot of overlap for this to work. So it's each pixel. This is essentially a process called dense point matching. Each pixel has to be imaged from several different angles in order for it to build, you know, to look for the patterns of where the overlaps are, both from a visual perspective, top down, and also the algorithm uses the 3D. It essentially builds the point cloud before it even makes the orthomosaic, because it's actually fitting things both in 2D and in 3D in order to figure out the orthorectification. There you go. So have fun, play around with that, and let us know how it works for you. So that's just a shot of the input, and there's the output, the orthomosaic and the point cloud. And I've got another workspace that I use for generating project folders. So that's another aspect of post-processing. So you can use FME to populate metadata, maybe an HTML table listing the missions, thumbnails, so different things that you can put out on a portal for people who want to review the mission data. So that's pretty much it. My main focus here was to show how FME supports integration with a third-party tool, in this case OpenDroneMap, which is free and open source, but there's lots of other tools you could use FME to integrate with as well, other proprietary tools, and both for data prep and post-processing. And both of us have been talking a lot about automation.
Yes. Basically, maybe a few key takeaways from this webinar. It's really important, really strong, where FME really strong is transformation capabilities. You saw how we can change data either natively in FME or using third-party tools. And we also showed how we can automate this process. Right, so the workspaces that I showed, I set them up last year and never touched since, but you can see that they keep working and delivering information for us. So, and what is really great about FME Hub and our examples, webinars that all these workspaces are available, and you can try and see how you can adjust for your needs.
Yeah. So yeah, I think we've seen with the way that raster imagery and remote sensed imagery and data collection has been automated. It's very pervasive now. Things that might have been imaged once every couple of years, now there's daily imagery, as we saw from Dimitri's example. There's ways to collect data from drones, and I think it's interesting. Even Dimitri, you mentioned cell phones. There's nothing magic about where the image comes from in this case. It could just be collected from a cell phone. And I was at a conference a couple months ago where they couldn't get a permit to fly a drone in Zurich, or it was in Switzerland. And so they just put an iPhone on a crane, and it moved along wherever the crane hook was going, like the top of it, the part that lowers the hook. And they just collected the data every day, mosaicked it all together, and they had a 3D model of their work site every day, and they could compare what was being built versus plan and look for problems. Oh, they put this in the wrong location or what have you. So yeah, there's so many different tools out there, so many platforms collecting data, and so given that huge volume of data, really it really begs the issue of automation. Nobody wants to sit there and have to do all this stuff manually. And then I think on the integration side, yes, FME has some really powerful transformation tools. And as Dimitri mentioned, things like Convolver, the object, raster object identifier, that's always being expanded. But then there's always going to be specialized things that FME might not do. And so being able to use FME to integrate with third-party tools, whether, let's say, via a REST API if it's online, or via Docker locally if you don't have web access. So there's lots of ways of doing that integration. So pretty exciting stuff.
Yeah, this Docker example, I found that's the first time where I see how I, for example, could use Docker, because before we were talking about that and I really couldn't understand why would I need a Docker container. And this example is really great. You have a really good example with this drone imagery, how you can basically get real orthomosaic just using a Docker container. So really great. Yeah.
And that, I mean, you can get as complex as you want if you want to read up on what that thing's doing, because it's actually a collection of a bunch of different libraries. But the nice thing about it, it's in that container, it's running on its own little Linux. And if you don't really want to know how it works, as long as you understand the input parameters, you can use it and benefit from the results. So that's pretty impressive. And this is a really lightweight notebook. That thing ran and processed about 10 images in 5 minutes. Not as impressive as the the millions of tiles that you did in 25 minutes. But if it's the data that you need for your, local application, then it's all good. So I think we got a couple minutes for questions, and I'll just say that I'm pretty impressed overall with what we can do with rasters with FME. That's kind of one of the things that I kind of came to SAFE to work on was rasters, and sometimes people are more familiar with the vector and 3D capabilities, and raster is kind of the younger brother that doesn't always get the attention. So I'm happy to be able to focus on that today. So thanks to Dimitri for your great examples, and Dave. I know Dave's on QA. Is there any interesting questions there that we can address before we wrap things up? I don't know if you have the question pane there.
How does one pay for FME engines when using Docker?
Well, the Docker itself doesn't cost anything, because in this case it's an open source image. So you would just be using the normal FME that you're working with anyway. So it doesn't consume an extra engine, if that's what you mean. Obviously, you need an FME engine just to run FME.
That's the last question is about Sentinel-2. Yes, it stopped working because on AWS stopped working, the reader, and my example, which does not use the reader, but yeah, stopped working because Amazon introduced pay-per-use setup. So we are working on this right now. So it will be available soon.
I see a question about I think it's about the search grid. So you just give it a starting point, and you just tell it what the length of one leg is. Let's say you want your tiles to be 50 meters apart, and then you just tell it the number of legs and the number of rows, and then it just generates that search grid. So you could just take that transformer and also just use it essentially as a Litchi writer, because it'll show you what the schema is for Litchi. And it actually shows, now it doesn't just generate the grid of points, but it tells the drone to stop, wait a second or two so that it's stable, take a photo, and then move again. So there's other instructions to the drone about what it's supposed to do at each point.
Here is one more question. What feature extraction tools does FME currently have? We can mention a few transformers. A couple of them would be a point cloud, why I'm saying point cloud? Raster expression evaluator, where you can process your raster for example, based on certain pixel values, make very simple, for example, black and white raster, which then you can turn into vector features with raster to point cursor or raster to polygon cursor. Or I use a lot Portrace Color. It's a custom transformer that uses Portrace, a third-party tool which vectorizes really nicely such rasters. And for me, adds the value that it keeps the georeferencing, which Portrace has no idea about. Then raster convolver is a really great one, because you can again pre-process your rasters for much better vectorization.
And the other one I'll mention before I forget is just the raster cell value replacer. And I use that a lot because what you can do is you can take a range of values and then essentially classify that. So let's say, for the simplest case in point, you could take 0 to 20 elevation and just call that 1. And so if when you're able to take a range of values and simplify it into one value, then that helps in things like extraction features or classification. So many of these you might want to use in combination. So the convolver, doing edge detection, for example, and then maybe the cellular value replacer to do some classification, and then maybe an expression evaluator after that. So it'll take a bit of experimenting. We don't really have out-of-the-box feature extraction, except for this new object detector. That's going to be interesting to see where that goes.
Yeah, but it still probably will extract just it will show where the objects are.
The location of where the object is.
That's I tried actually, similar to natural different vegetation index. I made that for water and extracted quite nicely generated all the hydrography for lower mainland using Sentinel imagery, using these transformers, raster expression evaluator, and portraits filter, and normalize difference water index transformer.
Yeah, and the other one that I did that was part of the raster, this raster talk for the World Tour, which we didn't have time to do today, was basically generating flood polygons.
Mm-hmm.
So if you have a flood level on a DEM, you can use FME to extract, essentially flood that DEM, and then that's using the raster to polygon coarser. All the areas below the water level then become a polygon, and then you actually have a vector polygon you can use to clip stuff and say, oh, this is going to get flooded.
Yeah, so I see that we are out of time. So thank you everyone for joining. Send us your questions. Download the slides and the examples, and please join us for the next week webinar where Tiana and I and Jake will be talking about PDF reading.
Yeah, thanks Dimitri for kicking us off today and those great examples. And yeah, thanks everybody for coming. Appreciate your time, and hopefully these are some of the building blocks that you guys can take and show us some of your interesting examples, and maybe you can present one of them on one of our World Tour stops or something like that. So yeah, thanks again for checking out, and do take a new look at how to use FME to process and integrate your raster data if you haven't looked at that recently.